lecture 35. In the last class, we were looking at the practical issue of stabilizing the band edge of a filter in the face of process and temperature variations. We all know that the band edge will be some number multiplied by something of the form Gm by C, where Gm is a representative transconductance in the filter and C is a representative integrating capacitance, right. It will be proportional to Gm by C, and please note that if you make many Gms on the same chip, then by virtue of matching they may all be off from the desired value, but they will all be off by the same percent, right. The same thing for the capacitors. Now, since all capacitors and all GMs are off by the same percentage, it follows that anything which depends on ratios of transconductors or ratios of capacitors or a combination of the two will largely remain unaffected even when temperature and process change. So for example, the quality factor of a biquad, which is inherently a dimensionless quantity and must therefore depend on the ratios of like quantities, will be unaffected by process and temperature variations. However, the band edge frequency, which is of the form Gm by C, will clearly vary with temperature. So, one way to mitigate this problem, I mean obviously you can see that this is a serious problem in the sense that if the Gm varies by plus minus 20% for example, and C varies by another plus minus 20%, you have a plus minus 40% variation in the band edge, which in most situations is completely unacceptable, right. So, there are simple and complicated ways of fixing the problem. The simplest technique is one which has been suggested in your assignments, right. So, we say that we do not want to make, I mean in principle at least we know that what we need to do in order to stabilize the band edge is measure the band edge, compare it with the required band edge frequency, and then somehow tweak the transconductors such that, or capacitors or a combination of the two, such that the band edge actually matches the frequency that you want it to be at. But that sounds awfully complicated. So, a very popular and a common way of doing this is to stabilize Gm with process and temperature, right. And how do you do this? This is through what is called a GM servo loop. A servo loop is engineering terminology for a feedback loop, right. So, when we say a GM servo loop, all that we mean is that the transconductance of the transconductor, right, this could be the differential pair, this could be the degenerated differential pair, whatever, the transconductance of the transconductor is equal to, if you want to make it constant, that constant must be available somewhere, correct. So, as we have seen in your assignments, this Gm is made to track some 1 by R, and it does not help if R is on chip, correct, because this R itself is varying if it is on chip. So, this R must be something external and must be, in principle 0 temperature coefficient and all this other stuff, right. It turns out that that is not a difficult thing to arrange at all, right. So, you can buy a discrete resistor and have it on the board, right, and the resistor is available with very tight tolerances, right, typically 1% or so, and if you get the right alloy, then you will find that the variation of the resistor with respect to temperature may be a very small number, right, which is completely not the kind of variation you would get with the transconductance of a MOSFET. For example, you might have seen that if you did not do anything special and if you bias a transistor at a constant current, then over the 0 to 70 or whatever range that you use for simulation, the transconductance varies quite a bit, right, okay, and that is because mobility changes with temperature, you know, all sorts of things. So if we somehow come up with a circuit which will make sure that the GM is the same as 1 by some R external, where R external is a stable quantity, then regardless of the temperature or process variations, we find that the GM through negative feedback is set to this R external, right. So if we use the same bias currents etc. for other transconductors, it then follows that all transconductors will be servoed to multiples of 1 by R external. Is this clear? And the conceptual idea behind how one might set GM to 1 by R external is as follows. You have a transconductor. I want to set its transconductance to be 1 by R external. Can you conceptually tell me what you will do? So I am going to draw a single-ended schematic for ease of drawing. We have some transconductance, okay. Obviously this transconductance must be tunable, otherwise if it's fixed then that's all, you can't do anything with it, right. So the implicit assumption is that the transconductance is tunable through some kind of knob. So in other words, for example, in a differential pair, what knob will you use to tune the transconductance? You can use the tail current source, okay. For example, if you had a degenerated differential pair, so if you had a differential pair, to tweak the transconductance you will tweak the tail current, alright. If you had a degenerated differential pair, what do you think you would do? You would have to tune this resistor. How do you electronically tune the resistor? I mean, this is a fixed resistor, this is a resistor. How will you change it electronically? So one way is to have a bank of resistors, correct. So for example, a tunable resistor is you take a fixed resistor and then put many of them in series, for example, and then have switches which are electronically controlled, which can remove or add resistance as you please, right. And how will you implement the switches now? Yes, you implement the switches as MOS transistors. So now you have, in other words, you have a digital word going in and tweaking the resistor. Of course, the control, how fine the resistor can change, depends on number of bits in the digital word, okay. So this is one very popular way of doing it. If on the other hand you want analog control of the resistance, what do you think you could do? Pardon? Yeah, that's what, voltage controlled resistor using a MOSFET operating in the triode region. So that's another way of realizing this character. And we notice that here it's particularly convenient in this case because no quiescent current flows through this resistor anyway, correct. So if you replace that resistor by a MOSFET, the MOSFET is operating in which region by default? Triode region. Why? VDS is 0, correct. So as long as this voltage is greater than the source voltage plus a threshold, the MOSFET will be on and will be operating in the linear region. And what is the, if this has a W by L and this is Vx and this is Vy, what is the resistance of the MOSFET? Yes, what is it? 1 by what is the transconduct? I mean, you should never say transconductance in a when the MOSFET is operating in triode with 0 VDS. What is the transconductance? What is the definition of transconductance? Okay, people, come on. In the linear region, what is the transconductance of the MOSFET? Okay, what is the equation of the MOSFET in the linear region? Yes, people. Mu n C ox W by L times VGS minus VT times VDS minus VDS square by 2, right? So this I'll make this approximate. So GM in the triode region is what? Mu n C ox W by L times. What is the transconductor? What is GM, guys? Times V DS. Okay. What is GDS? Or mu n C ox W by L times VGS minus VT. Okay. So what is the resistance, equivalent resistance of the MOSFET if it's 1 by GDS, which is 1 by mu n C ox W by L times VGS minus VT. VGS in this example is Vy minus Vx, and therefore it's clearly seen that if you change VGS, the R changes. If VGS increases, the R decreases. But one assumption we have made in this analysis is that we have neglected the VDS square term. Okay. So strictly this speaking, this resistor is not very linear, and therefore that will lead to distortion. But I mean, unfortunately, if you want an analog voltage variable resistor, the MOSFET is the only one at our disposal, and it is nonlinear. Tough luck, that's all. So to prevent, I mean, to prevent this linearity of the MOSFET getting in the way, a very common method is to have a switchable bank of resistors, as indicated, as you all guessed in the beginning, right? The switches, of course, are fairly straightforward to implement. You just use MOS transistors and turn them on or off. Okay. So yeah. Yeah. See, this feedback is not. Pardon? Oh, what feedback are you referring to, Ashwin?
We are trying to match the GM with 1 by R external.
Correct.
So till it matches, it will anyway be tweaking the R.
So the question asked was, since we are going to have a resistor servo loop to match the resistance of the, I mean, the GM of the transconductor to 1 by R, does it really matter that the GM is nonlinear? Do you understand? Okay. It's a good question. To answer that, let's get through the entire feedback loop and see if this linearity of the MOSFET is a problem. Do you understand the question?
Sir, but sir, the resistance, if we need to operate with some current will be flowing through the resistance, and that if it is not in a linear region, then that will eventually make it some distortion will come in, right?
Yeah.
So we want the resistance to be linear.
Which resistance?
That
yeah. So that's correct. So anyway, we'll get through to the reasoning and then understand if the MOSFET being nonlinear is a real problem or not. Okay. So we understand that regardless of how we implement the transconductor, at this point it must have an input port and output port where the output current is GM times the input voltage, and some knob to tweak it. That could be a digital knob where you have a bunch of bits going in and tweaking the resistance and thereby the transconductance, or an analog knob where you go and tweak the voltage in the gate and then the transconductance varies, or you tweak the current in the differential pair and the transconductance varies, and so on. I mean, every transconductor that you come up with will invariably will obviously have to consist of some knob like this, right? Because transconductance depends on either on a resistor or a combination of bias current and resistor and so on. So by tweaking everything, you will be able to change the transconductance value. Okay. So conceptually, what do you think we should do if I want to make GM time equal to say 1 by R external. Conceptually, what should I do? If you are in the lab, what will you do?
Measure the current output for the same voltage
Yes, and
across the resistor and one
very good.
resistor and the GM,
Okay.
and compare it and tweak the knob such that the current through the resistor is matched.
Yeah. So basically, you know, the idea is very simple, right? I will put a known voltage across the transconductor, measure the current, okay. Compare that current with the current that would flow through a resistor of value, you know, no, not 1 by GM,
1 by
R external, right? And look at the difference in the two currents, and then if they are not the same, I know that the GM is off. It's either more or less depending on which current is more or less. Go and tweak the GM, right? In principle, it's very straightforward. Now instead of comparing currents, I can convert those currents into voltages, compare voltages, you know, a whole bunch of things. But conceptually, this is what is happening. I will put, for example, I will put some Vref, right? In which case, this current becomes GM times Vref, all right. Now, instead of comparing currents, okay, I can compare voltages instead. So, if I pass this through R external, right, what will this voltage be? Pardon? This will be GM times R external times Vref, correct? So, if I want GM to be exactly equal to R external, what should I do? I will compare this voltage with Vref and then go and tweak GM. So, in principle, what I would like to do is all right. The signs on the op amp, of course, have to be, I mean, it depends on how the tuning knob controls the transconductance. I mean, it's not inconceivable that you tweak the tuning voltage and the transconductance decreases, or you tweak the tuning knob and the transconductance increases. Depending on that dependence, you have to go and appropriately set the signs on the op amp so that this feedback loop is a negative feedback, correct? And whenever you have a negative feedback loop, you also have, I mean, what do you need to worry about? Stability, right? So, I mean, you also need to therefore compensate this loop. Typically, something that will simply work is just to put a large compensating capacitance here, okay? And this becomes Miller I mean, very similar to Miller compensation. Okay, but you can work out your favorite compensation scheme. All that you need to understand is that it's very likely that you need a compensating capacitance, because see, another pitfall is that this external resistor by definition is external, correct? So, the wire, that node on the chip will have to go through bond wire, it will have to go onto the PC board, and then there will be a PC board trace, and then go connect to the external resistor, which is physically a bulky quantity, a bulky phenomenon, right? So, that means that, you know, this whole path there is going to be a lot of capacitance. So, in other words, this parasitic capacitance is going to be non-negligible. So, if you are not careful and if you run simulation and then you find that I need in fact I don't maybe I don't even need compensating CC compensating capacitor, it seems also stable and nice, right? Then when you build the chip and then it comes back, you will find that thing oscillates because you forgot to account for this character, right? Now, if your servo loop is oscillating, then what happens to your entire filter? It doesn't work at all, simply because why? All the GMs are getting this same control voltage or control current or whatever quantity that you have. Does it make sense? Okay. So this servo loop, this is the basic idea behind the servo loop, which goes and controls the GM. And please note that regardless of process and temperature, right, if the negative feedback loop is working, GM times R external times Vref will always be equal to Vref, which means that GM will always be equal to 1 by R external. Okay, which which basically means that the negative feedback loop does whatever it takes, okay, to make the current does whatever it takes to make the DC voltage flowing through R external or the DC voltage across R external to be exactly equal to Vref. Now let's now if this GM was digitally controllable, what do you think we'll have to do here? I mean, so in other words, if this was digitally controllable, all that will happen is here there will be a digital state machine which goes and connects the what do you call figures out the states of the switches, and I mean there must be some kind of crude ADC inside, right? And so you can see that the thing becomes a little more complicated. However, the advantage of having digital control is that these lines which go, right, are all digital lines, right? So they are not susceptible to, I mean, because of the inherent nature of digital logic, if there's slight jumps on these, if these lines go all over the place because they're running to all transconductors, so it's not inconceivable that they pick up a lot of noise, right, from interferers and so on the chip, right? And so a little bit of pickup will cause absolutely no harm if this control is all digital, whereas if you have a sensitive analog line going all over the place, then you now become, I'm not saying it's impossible to design, but you have got to be very careful, because noise coupling onto this node basically modulates the transconductance of all the transconductors in the filter and then can cause a mess. You understand? All right. Is it another question I'd like to ask you is it necessary that Vref be an accurate known voltage for this loop to work? No, because every time we are comparing GM RXT times Vref to Vref. So Vref cancels out in the whole bargain, correct? So which means that it's not really critical. All right. So now since it's not critical, can we make Vref equal to 0? No, right? Because clearly, I mean the loop gain function depends on Vref, right? Because a small change here causes the GM to change by some amount, but the change in the current is the delta GM times Vref. Does it make sense? If I yank this voltage, the GM changes by a little bit. The change in the GM is responsible for a change in the current, right? The amount of change in current is basically directly proportional to Vref. Therefore, if you set Vref to equal to 0, then obviously there is no loop to speak of. You understand? And so, can you also comment on small values of, would you like to use small values of Vref or large values of Vref? Why? Okay, so one might be tempted to use a very large Vref to make the loop gain high, right? And this is indeed a good thing to do. However, what should you bear in mind when you make Vref very large? The linearity of the transconductor, because what the servo loop is doing so once the servo loop has settled, if the GM was perfectly linear, then as you tune, what happens to, this is I out of the GM versus V in, right? If the transconductor was perfectly linear, as you tune, as you vary the tuning knob, what happens to this curve? The slope keeps changing, right? But this still remains a straight line. Okay. So in steady state, if the transconductor is perfectly linear, this I out, rather I out times R on the y axis will be exactly equal to Vref. Okay. All right. But unfortunately, a real tunable transconductor, whatever we have seen, are all transconductors are fundamentally nonlinear because of transistors in them. The only difference between various transconductors is how nonlinear each one is, right? So in principle, each a nonlinear transconductor, for example, is perhaps doing something like this. So then what is the servo loop doing? Yes, Ashwin.
Try to fix the other curve at the VF.
You at the equilibrium point when the servo loop has what do you call this thing has settled, then we find that the servo loop, all that is trying to do is keep the voltage across R external the same as Vref, doing whatever it takes to it does whatever it takes to do this, right? Now this is a situation where the small signal transconductance of the transconductor, the blue curve, right, has the same slope at the origin as an ideal transconductor, which is a perfectly straight line, right? But clearly, because of nonlinearity, the transconductance is saturating, isn't it? Which means that if you put in Vref, where Vref is large, the actual current coming out is not exactly the small signal slope multiplied by Vref. The actual current is only that much, right? So what will the servo loop now try to do?
Rotate the ground counterclockwise so that
It will try to increase the transconductance, right? It will tweak that knob to make the output current coming out of the transconductor times R equal to Vref. So that's only possible if the slope is somewhat high. You understand? So now the absolute current coming out of the transconductor is Vref by R, right? But that is not the same as the small signal slope. You understand? So what is the moral of the story? You can't go crazy with making Vref very large. That's what I mean. You need to be make a good engineering judgment and figure out how large a Vref you will use. If you use too large a Vref, we see that nonlinearity causes a problem. However, on the other hand, if you say, okay, I'm going to use a very small Vref, then what are the problems caused by a small Vref? The loop gain will be small, okay, which means what? So what if the loop gain is small? See, please note that the speed of this loop doesn't matter, right? Because process variations and temperature variations are very, very long term phenomena. Okay. There will be a lot of static error, because why? The transconductor, every transconductor will also have what is called offset, and I haven't discussed that in this course, but what happens is that so far we have assumed that both the halves of the differential pair are exactly identical, right, or matched. In practice, the transistors will be slightly different, and you can show that even when the two, in that case you can show that even if the two inputs are shorted, right, ideally you expect zero current coming out. In practice, you will find that there will be some current coming, right, even when there is zero input. That's because of mismatch inside. That can be represented by some offset voltage in series with the transconductor. So that even when Vref is 0, the output current coming is V offset times Gm. V offset is an unknown quantity. So, so if you make Vref very small, right, the current coming out of the transconductor is not just simply Gm times Vref, but Gm times Vref minus V offset. So, you want that error current to be as small compared to Gm times Vref as possible, right. So, which is why you do not want to make Vref very small. On the other hand, you can't make it very large because of issues with nonlinearity as we just discussed. Yes, sir.
Sir, finally we are comparing the omega naught cutoff frequency H.
Yes.
Reference,
Yes.
Giving the feedback.
Yes.
So in case my Vref is large, I agree that the curve will shift towards, like, it will be upper half and the Gm will not be same. But even if it is nonlinear, as long as we are comparing the omega naught,
Please note, this got nothing to do with omega naught. This is just this loop. All this is doing is keeping Gm, making Gm equal to 1 by R external. We have not yet come to the fact that we have not even come to the point of stabilizing omega naught. Correct? All that we have done so far with the servo loop is this Gm is now stabilized. Okay. Now we still need to take care of the capacitance. Thankfully, what happens is that in most processes, the capacitance can vary, right? By the nominal will be something, but you may be able to get something which is plus minus within plus minus 20%, right? However, once the chip is made, the variation in the capacitance or the temperature coefficient of the capacitance is very small and often negligible. So then, what would you do? Let's say you were expecting C, but you got 1.2 C, right? So what if Gm is servoed to 1 by R external? How will you be able to get the band edge is now off by a factor of roughly 20%, correct? Okay. Now how will you fix the problem? Yeah, so you instead of having this, you make it 1.2 Gm, right? And so in other words, you have some amount of what you call fixed programmability built in, right? Or you vary R external by 20%, and once you do both these, what happens? If you do it at in the factory at calibration time, right? The band edge is set to the nominal frequency, whatever omega naught you wanted. Then the only thing you need to take care of is, now this thing is, you sold it, right? You can't keep sending an engineer every time, some guy switches on a cell phone to tweak the filter band correctly, right? So, but you've set in the factory, you've set the nominal corner frequency to be what you want or sufficiently close to it. Okay. Now, what is the servo loop doing? So, now all that the servo loop is doing is taking care of variations in ambient temperature, and sometimes as the gadget is being used, aging also causes parameters to change. For example, mobility could change and so on. Sometimes stress causes mobility to change. All sorts of things, right? But the negative feedback loop will go and always make sure that the transconductance is what you want, which has already been accounted for a variation in the capacitance, right? So all that you need is a one-time tweak, and after that you are ready to go. Yes, yes.
But that doesn't prevent me having VCM ref, that Vref as large voltage, because here we are assuming my black curve is fixed. What if
No, there is no black curve at all.
No, that graph, the black line.
The black line doesn't exist. It's so the this thing of an ideally linear transconductor.
So like that whole thing can also shift because of R variation.
There's nothing there to shift. The black curve doesn't exist. The black line doesn't exist at all. It is just a hypothetical illustration of what would have happened if the transconductor was tunable and perfectly linear.
So with the change of R, what is going to happen in this?
Pardon?
With the change of R external, how this curve is going to change?
This curve will not change. All that will happen is that if R external changes, I times R external, I mean this curve will get expanded in the vertical direction, right? You understand? That's all. Okay. All that I am saying is that once you use the servo loop, right, the small signal transconductance, which is different from, if you have a nonlinear transconductor, I out divided by V out, V in is different from d I out by dV in. The slope and the ratio of the small signal slope and the absolute current and voltage are different if the curve is nonlinear. That's all. Correct? Okay. And you know, I mean, so many of these so-called servo loops can all be, you know, classified into, you know, all various implementations of transconductance, various implementations of the error amplifier, right. You will find that almost all those circuits can be clubbed into this basic idea. All right. Now there are some clever circuits which are not very obvious. You know, one of them, couple of those circuits are given in your assignment, right? Where, right, it's not very clear how this fits into the whole. I mean, this is conceptually what it is, but those circuits also give you magically a transconductance which is 1 by R independent of process and temperature, right? But there seems to be no servo amp, there is no voltage reference, everything is happening inside, right? And those circuits are not very obvious to deduce from first principles. I mean, now the circuits have been invented and then we analyze the circuit and then we figure out, yes, this is what happens. But it's not immediately, I mean, if I was starting off from scratch today, even I'd probably be come up with some circuit like this rather than those simple 4 transistor circuits, right, which the derivation of which is not very obvious. Is that clear? Okay. Now, all right. So these often, I mean, all these family of circuits also go under the name tuning circuits, right, or resistor servo loops. Okay, or something to this effect. Right, it's and as we were discussing towards the tail end of last class, it's possible to come up with more complicated schemes where resistors don't appear in the picture at all, where we actually measure the band edge, right, and then tweak the knob of the filter such that the band edge is what you want at a frequency that you want it to be. Okay, there are several ways of doing it, right. So let's assume you have a high order filter. So this will come under more exotic tuning schemes, and given that they're fairly complicated, no wonder nobody uses them, right? All right, and all, I mean, most practical chips you just go with the resistor servo and live with it. Okay, but this is good fodder for writing a lot of papers. So let's say you have a high order filter and you want to tweak its band edge to some desired frequency. So what do you think we can do conceptually?
Control the GM of
Of course, it's understood that the center frequency or the band edge of the filter is variable. By a tuning knob, perhaps some tuning knob which controls all the GMs. What else? So in other words, all right, we all know that we have some knob which will tweak the bandage over whatever range we want. Okay.
See the face of the output.
Okay, we see the phase of the output. So then what?
No, if you know approximately what is the center frequency, you sweep the input frequency in that range, and then you put a phase detector between the input and the output. See when that is becoming 90 degrees, and then there will be some error, that phase error. Depending on that phase error, you correct this.
Okay, so so one suggestion is measure the phase difference between the input and output and see when it's 90 degrees. Unfortunately, that doesn't quite work for a high order filter, because if let's say you have a fifth order filter, right, the phase goes from where to where? If you have a fifth order all pass, all pole filter, the phase varies from 0 at DC to 5 times pi by 2 from over a frequency range of 0 to infinity. Right, now if you are looking for 90 degrees, now this 90 degrees happens 5 times. You understand? So any phase detector will get totally confused as to what the hell is happening. You understand?
So we approximately know the.
Yeah. So then this thing is that hopefully you know the frequency in a sufficiently close ballpark. Unfortunately, this plus minus 40% kind of thing, right? This is not sufficiently close, because where do you think the phase varies rapidly in a filter response? At the passband edge is where the quality factors of the biquads really become very high. If you have a very sharp filter, the highest quality factor biquad will also will have a center frequency around the band edge, right? So the quality factor of the biquad is high. We know that the slope of the phase is very rapid at that point. So you will find that the phase quickly changes around the band edge. So you could still be in gross error if you try and force this 90 degrees.
We can go for a group delay.
Yeah, of course. See, you can go for very complicated measurements, like saying, okay, I will have an oscillator whose frequency goes all the way from 0 to infinity. Go on stepping up the oscillator, measure the magnitude response, right? Then plot the curve, look at the curve in principle, go and tweak the stuff, right? And by the time you have done that, your part is obsolete, right? So all is not. In principle, this works, but the question is to just find one number, which is the center frequency of the filter, or something which is proportional to the cutoff frequency. Do I need to do all this?
If it is a low pass filter, then give a step input.
Okay.
And if the bandwidth is too high, you can measure the raise time.
Okay.
And that raise time will give you some idea about your bandwidth.
Sure. Okay. So the next suggestion was you put in a step input, right? And we know that the only thing that's changing is the filter band edge frequency. The shape remains the same. So if we measure this, say for example, the 20 to 80% rise time of a step response, then
It will give you approximately.
it will be related to the band edge frequency in some way, and then you can use that to go and tweak, right? Now you converted this whole thing into something. You now need adequately high resolution for measuring the rise time. You understand? That also seems like complicated business, right? So along with the filter, you have to ship a whole oscilloscope along with it, right? That's not very practical, right? Okay. Though in principle it works. For example, if I was in the lab, this is what I would precisely do. All right. I would either if it is a high order filter, and if I knew that this is for example, a fifth order Chebyshev filter, I just needed to find the center frequency. I don't have to bother with having a sine wave source which can go all the way from 0 to infinity. I have a step response, right? In principle, a step is something which has got frequency content all from 0 to infinity, isn't it? So I don't need separate sine wave sources. I look at the step response, look at the 20 to 80% rise time, and given it's a fifth order Chebyshev filter, I know the relationship between the 20 to 80% rise time and the bandwidth, and I just go and it's just a lookup table, and I will have to figure out what the omega naught is. Fine, right? But that's not quite practical here. Yes.
So from the spec, I will know what is my omega naught.
No, that is what I want my omega naught to be, right? I don't know what the omega naught is. It could be off by plus minus 40%, which is basically off by a factor of 3, right? It could be you want 1, you get 0.6 or 1.4. This is like 2.5 times variation. Come on, people.
So, what's the time constant? The time constant will be.
What is time constant now? You have a high order filter. What is the meaning of time constant?
3 dB. Give a step and see when it.
That is the same thing as what he said, right?
Reaches around some value.
Which is exactly what he's saying. Give a step, see where it reaches 20% of the value, where it reaches 80% of the value, subtract the two. It's basically rise time measurement. Anything else we can think of? No, see, please note that, see, in life there is no, the solution doesn't exist. There are many ways of doing the same thing, right? So there is nothing to feel, sorry about, say, thinking maybe this is the wrong answer, right? Every answer is valid. We have to discuss it, figure out whether it makes sense or not in this particular application and move on.
What about finding the 3 dB point?
Yeah, okay. So then the next thing is find the 3 dB point. How will you find the 3 dB point?
Give input the omega, give sine wave of same omega naught and measure the amplitude at tau and compare it.
Well, yeah. So that is one suggestion is, okay, this is the filter, for example. So let's say, when I say I know what frequency the center frequency must be, I must have some electrical representation of that quantity, right? One way of representing that is to have a sine wave with us, which is at omega naught, the desired banded frequency or a multiple, right? Okay, so then what he is saying is measure the amplitude, right? And then we know that the amplitude must be so much. It is not that much. So you can go and tweak. But then what problem do you run into there? Clearly, if the magnitude is not monotonic, right? For example, let's say the filter was like this, right? So at omega naught, clearly the frequency is the amplitude is not what we want, correct? All right. You don't know now which side to tweak. You understand? So that's a problem. Okay. What next?
So if this is a cascade of bicod, then we know that the last bicod is responsible for the last thing.
Okay, one at a time. Okay.
Like if we know that this is a cascade of bicod,
yes,
we know that the last bicod is responsible for the last thing.
Okay.
So we can tune only the last bicod.
Okay. Yes, Ashwin.
Sir, we do know which direction we have to go now, sir.
Not really.
The 3 dB point is always lower than the 1
Well, in the okay. So let's say you're here at this minimum. Okay. What will you do? You know that you're not at the 3 dB point, right? So you're saying I will simply increase the stuff. Yeah, sure. That's a reasonable way of doing it. Okay. All right. What else do you think of? What else can you think of?
Like if this is a cascade, so we know that like one will be drooping like this, second one will be like
okay.
this, third one will be like this.
Okay.
So we know that the last one is basically responsible for this.
Okay.
So omega 3 dB. So we can tune that.
Okay. So all right. So let me kind of discuss why. So so one is what he suggested is to use the magnitude response at a known frequency, right? You know what it's supposed to be, you know what it actually is. If you choose that known frequency cleverly, you know the right direction, and then you go and tweak slowly, right? But it turns out that magnitude measurements are always erroneous, okay? And especially if as we have seen in the case of measuring omega naught of a second order system, it always always more accurate to measure phase than measure amplitude. The problem with a high order filter is that this phase is doing all sorts of wild things because of the large number of poles. So what do you think you can do? If you had only 2 poles, or if you had a second order system, then the problem wouldn't be there at all. So what could you do? There are 2 things you can do. One is to say I will only look at one of the biquads, correct, and do phase difference between the input and output, find the frequency at which the phase becomes, I'll measure the phase difference between input and output. If the phase is not 90 degrees, or rather if the phase is less than 90 degrees, I know that my omega naught is too high or too low. It's an all pole system, let us say second order all pole system, right. We know that at omega naught the phase is exactly, for the low pass response, the phase is exactly 90 degrees behind. Okay. Now if I measure the phase, right, and if I find that it is 45 degrees, does that mean that my omega naught is higher than my desired value or lower than my desired value? So at omega naught, if I measure the phase and I find that the phase is less than 90 degrees in magnitude, then it means that the omega naught is higher, and I keep reducing omega naught. On the other hand, if I find that my phase difference is larger than 90 and less than 180, I know that my omega naught is too low, I need to increase it. So all that this needs is a simple negative feedback loop which looks at the phase difference and tweaks. You understand? All right. So second order phase measurement seems very clean. So we can do one of two things in a high order filter. I can take, for example, one of the biquads of the high order filter, right, and then put in a sine wave at omega naught, right. The output will also be a sine wave. I measure the phase difference between the input sine wave and the output sine wave. How will I measure the phase difference between two sine waves at the same frequency? You can put a multiplier. Unfortunately, and if you multiply the two, now you also start becoming sensitive to the amplitude of the two sine waves, correct. So if you want phase difference but you do not want to be sensitive to amplitude, what do you think you can do? You understand? So you have A1 sine omega t and A2 sine of omega t minus phi. You want to measure phi, right? If you multiply the two, you will not only get the the DC term will not only consist of cos phi, right, but will also consist of A1 A2, which is a pain because the A2 now depends on the omega naught also, correct. Now A2 is the output of the filter. Okay, so what do you think we can do? Okay, make a wild guess. There's no. Pardon? That's too complicated. Okay, I mean that's probably okay. So digitize and do a digital phase detection. What is the easiest way of digitizing and doing digital phase detection? Pardon? Yeah. So you convert the sine waves into square waves, right? And then you multiply. Multiplying, a digital waveform is equivalent to using an XOR gate. So basically, what you do is you put a comparator here, you put another comparator here, you use an XOR gate, right? And the average value here is an indicator of phase difference, okay. And if the lower level of the comparator is -1 and the higher level is +1, then if the two square waves here are 90 degrees out of phase, what will be the average output of the XOR gate? Pardon, wait a minute. Should be 0, I say. Alright, so this is one square wave. This is 0, this is 1 and this is -1. The other, this is how much? 360 degrees. So 90 degrees out of phase means what? Yeah. So at 90 degrees, what will be the average value? It will be 0, correct? So all that you need to do is take this low pass filtrate or compare the DC value with 0 all right. Use the appropriate signs for the op amp, all right, and go and tweak. Pardon? Correct. So that will depend on the change in the I mean how this knob influences omega naught. You understand, the sign of the op amp is to be fixed depending on the relationship between the control at this knob and the actual change in the frequency. You understand? And this feedback loop must be a negative feedback loop. I mean, this is no point mugging up this kind of stuff, right? This is, think about what you will do in the lab, right? You would go sit, measure the phase difference and tweak the knob in the right direction. That's all. That's all this is doing, right? Okay. And whatever control voltage or control current that is developed for biquad 3, you supply the same thing to all the biquads in the filter, assuming it's a cascade of biquads, and you know, by virtue of matching, you will find that this will be tuned. I mean, this will have an omega naught which is tuned to the desired value. Right? As you can see, this is obviously a lot more complicated affair. You understand? But it does not require an external resistor. All that it requires is a stable clock frequency. I mean, you can't get away from having something which is stable, right? You understand? If everything in the planet is varying, then you know you also vary along with the planet. That's all, right? If you want something fixed, you better have something fixed, either a constant current, constant resistance, constant frequency, something. But something must be fixed. You can't have everything varying. So here the idea is that anyway in a big mixed signal chip, you have the clock which goes to all the digital this thing. So in principle, you don't need anything extra, right? You can just take that, the clock which is clocking your microprocessor, for example, that will be, you know, stable. It will be generated from a crystal, so it will be very accurate and blah blah blah. So you can use that as the reference, and you know this loop will basically take care of variations of omega naught. So now you don't have to worry about tweaking this whole thing in the factory at startup, right? You don't have to calibrate in the factory. So this is called, this is one approach which is called the master slave okay, master slave filter tuning. This is called what? This biquad, which is a representative of the high order filter, is called the master. Alright, and this fellow just follows the instructions given by the master. So this is the slave.
So here, do you assume that all the biquads which make up the higher order filters are same?
No, they are not the same. I am just saying they are all, if omega naught of one changes, the omega naught of everything will change.
In the same way?
Yes, that's reasonable, right? Okay, does it make sense? All right, can somebody think of you know, of an efficient way of doing this without having an extra biquad?
So we can look at the last biquad.
You choose. I mean, you can do this instead of I mean having a separate biquad. You can do this kind of phase locking approach to one of the biquads in the filter. However, when you are doing this, obviously the filter can't be used. You understand? I mean, because you need the sine wave input, right? There are many systems in which filters are not being used for some time. Okay, for example, a lot of these, some of these wireless communication standards, you know, you are either transmitting or receiving. You are never doing both at the same time, right? So in which case, when the transmitter is being used, you can go and tune the receive filter bandwidth, right? You know, and hold the control signal that was generated, right? And then use it in during the receive burst. Okay, so this is all, and in which case you can actually save this whole biquad 3 and so on, all that you need are a couple of comparators and an exclusive OR gate and some servo amplifier like that. Okay. In some situations it may absolutely not be possible when you are always receiving, and then obviously this option is not possible, in which case you would have something like this. All right. Okay. Another thing that you can think of, so this is also often called the VCF technique, right. So VCF stands for voltage controlled filter. Okay. This and the master are voltage controlled filters, and then you figure out what voltage you need to give them so as to have the right. Okay. So I think I will stop now.